Well, welcome everyone. Let's do some more set theory, shall we? Before I begin with the Erdős-Dushnik-Miller theorem, I'd like to say a few things about these partition theorems that we have been talking about. And you saw a few glimpses of what I'm going to say now in some of the exercises and the quiz questions. You may very well wonder why partition theorems? Because, well, where do they come from? What's the origin? Well, if you look at Ramsey's paper, you wouldn't know that there was any combinatorics in it. Because the title of the paper is A Problem of Formal Logic. And when you count the pages, you will find that Ramsey's theorem occupies the first 6 or 7 pages, and the rest of the 23 pages is devoted to a problem in propositional logic, where he looks for criteria for satisfiability of all kinds of formulas. And he needs this combinatorial principle to be able to come up with a characterization of that. It's worthwhile, if you're interested in that kind of thing, to look up the paper and see what the application is all about. And it is of the kind that you are looking for a good homogeneous set for a certain partition, and the satisfiability is a consequence of that. So that's one origin of this Ramsey theory. Another origin and this is definitely for the beginning in the finite realm. Esther Klein showed that if you take 5 points in the plane, no 3 on one line, then 4 points will form a convex quadrangle, of a foregone, so to speak. So no matter how you put 5 points in the plane, there will be no 3 on a line, then you will find 4 that will give you a convex set. And what happened after that, the 3 of them, or certainly Erdős and Sekeres, they discovered that for every n, there is an n, and that will be a capital N, such that among n points in the plane, no 3 on a line, you can find a convex n-gon. So you can find endpoints, little endpoints that together form a convex set. And so how on earth did Ramsey theory enter into this? Well, their proof was you need if you take the arrow notation of last time, the compact notation for Ramsey's theorem, you need that the big N arrows the little n, 5, 2. Now, I didn't quite define what it means to arrow to different numbers, but you can imagine what this means. If you have n points and you partition the pairs into two sets, one of the colors will have a homogeneous set of n points, or the other color will have a homogeneous set of 5 points. And we'll come back to this form in a moment anyway. Another, actually, no, sorry. I almost forgot. That shouldn't be a 2, that should be a 4. The other, there is another proof of this theorem that uses that n arrows n 3, 2. So you, in the first case, you partition the 4 tuples and find a homogeneous set of size n or one of size 5. In the other, you do it with 3 and 2 colors. The existence of this number n can be proven using the compactness theorem and König's infinity lemma that we'll talk about in a moment from Ramsey's theorem. But you can also give explicit bounds for these numbers, and that's there's a whole industry devoted to that kind of thing. For those who know their general topology, okay, so this is, shall we say, finite combinatorics, Ramsey's theorem itself. What about the larger one? Well, applications of the Erdős-Dushnik-Miller theorem usually are quite specialized, and you need to know the background of the field that you're talking about in order to appreciate the application. But here is one for those who know their general topology. This is one of the earliest applications of this idea in general topology. So if you don't know, if you know what this means, wonderful. If you don't, you can ignore it for the moment or look up all the definitions and see what it's all about. If you have a Hausdorff space, okay, first countable. You could almost think of a metric space. It means that there is a local base, a neighborhood base that is countable. And if you think of metric spaces, the balls of radius 1 over n would be of that nature. And what we generally know call CCC, which means every pairwise disjoint family of non-empty open sets is countable. Okay, so that's a whole mouthful, but this is a property that you can think of when you're talking about topological spaces. It's sometimes very useful to have, and certainly if you ever go into forcing and stuff like that, the CCC is an important property to have. So if you have a Hausdorff space, that happens to be first countable, that happens to have this sort of smallness property for families of sets, then the cardinality of X is at most 2 to the L of 0. And you may wonder where that comes from. Well, it goes by contradiction. You suppose X has more than continuum many points, and then the Erdős-Dushnik-Miller theorem will help you violate the countable chain condition. As this CCC is, it's an abbreviation of countable chain condition. And for those who want to know more about this countable chain condition, there is another result about these chain conditions. If you have, let me, where's my eraser? Suppose you have topological spaces that have this countable chain condition property. Then what about the topological product of those? Well, all families of non-empty open sets have cardinality what? There is 2 to the L of 0 again. If you take finitely many CCC spaces and you try to say, well, maybe the product is CCC again, no, the best you can get is that the cardinality is at most 2 to the L of 0. But it has the interesting consequence is that once you have proven this, it becomes true for all possible products of CCC spaces. But that needs another piece of combinatorics that we didn't talk about. You may also remember that in the quiz, there was a problem about a partition of the rational numbers with a bijection between the rational numbers and the integers. I'll repeat. What that says, and we had the partition that says the f of x and y was 1. The partition was this: if you take a bijection between the rational numbers and the integers, you will say that the color of a pair is going to be 1 if, suppose, say, the mapping is order preserving on the pair, and if it reverses the ordering, we'll give it color 0. Now, what is a homogeneous set? Well, homogeneous means F is order preserving or F is order reversing. And that gives you an answer to the question, to the quiz question, because I think the only set that could possibly be homogeneous was the one that could be isomorphic to a subset of the integers. All the other three could not be isomorphic to a subset of the integers. And that is what this theory also helps you look for. Find, say, large sets where mappings have certain desirable properties. So we want an isomorphism. How far can, how big is the set that we can get that's an isomorphism? Well, Ramsey's theorem says you can always get an infinite set on which the map is order-preserving, which could be useful in various circumstances. Anyway, those were some of the applications that I wanted to mention of this partition stuff. And I think you could almost say that most of them are encapsulated by what Ramsey was doing with the satisfaction problem, because very many of these things can be cast in, say, a language of formulas or things that are very much like it. Okay, I just said to look at the Erdős-Dushnik-Miller theorem. That's a whole mouthful. The paper where it appears was written by Dushnik and Miller, and they have a proof for the regular case, and they very profusely thank Erdős for the proof of the singular case. And I wanted to do this theorem to give you at least one case where a theorem has a relatively easy proof if the cardinal is regular, and a quite complicated proof when the cardinal is singular, just to help you appreciate regular cardinals a bit more. What does the theorem say? The Erdős-Dushnik-Miller theorem. There are books where the only attribution to the theorem is Erdős, but okay, it's in the paper by Dushnik and Miller. If kappa is infinite, then kappa arrows kappa L of 0, 2. So this is a lopsided partition theorem. It's not saying we're going to find a homogeneous set of that particular cardinality. It means that if F goes from kappa, the pairs of kappa to 2, then there is a homogeneous set, but H is 0 homogeneous and or the equal sign is no substitute for the word is. So this is, like I said, a lopsided partition result. We have a coloring with 2 colors, and you can cast this in the language of graphs, of course. We color the lines in the complete graph of cardinality kappa with 2 colors, red and blue. And there will be a homogeneous set for red that is full size kappa, or there will be a homogeneous set that is for the color blue, but that's only countably infinite. That's the best you can get. We have seen that in many, many cases, we don't get, say, kappa arrows, kappa, kappa, 2 to the L of 0 doesn't even arrow L of 1, L of 1, 2, for example, as we have seen. Okay. I'm going to give a proof for the regular case, and I'm going to give a proof for the singular case. And There is something to do for you in the group interaction, because you can actually take the singular proof that I will give in a moment and turn it into a rather easy regular proof, so to speak. But let's get underway, shall we? Okay, so we have our partition, and because I really like to talk about colors, and I'm going to use the colors here and there in a few pictures. We look at R, those are all the pairs that become, get color 0, red, and blue will be all the pairs that will get color 1. And
excuse me, I have a question.
yeah.
You say H is 0 homogeneous or H is 1 homogeneous above the page. I assume 0, 1 relates to values of 2. But how is 0 and 1 prefer that in one case cardinality of H is kappa, in the other case cardinality of H is out of 0? So what's the difference between, I mean, they're the same, they're just 2 different colors.
Well, the difference between the if we take a partition like this, we can prove that either there is a homogeneous set of size kappa with one color, or a homogeneous set with the other color that is countable. We cannot, because you will see in the proof that we will assume at one point, suppose all the 0 homogeneous sets are of cardinality less than kappa, then the only thing we can manufacture is a 1 homogeneous set of that is countably infinite.
I see.
So it's not so much that we will that we can predict which of the color is going to have the kappa, the size, sorry, the homogeneous set of size kappa. If we say that color does not have any big homogeneous sets, then the other color will have a certain nice property.
Okay, that makes sense.
Yeah. So we need this notation here. The red, so the red of alpha is all the betas such that the line between alpha and beta is red, and the B of alpha are all the betas such that the lines are blue. And so now we go to our first case, and and I'm going to do exactly what I just said. Assume suppose we are unlucky and we only have very small red homogeneous sets. And so what are we going to do now? Well, we're going to try and we find an infinite set that is blue homogeneous. That's it. And you will see that basically the proof sort of dies down after you have done this. Okay, so let's see what we will do here. This is not quite the proof that is in Jech's book. I got this from another source, and it's interesting as well. Okay, another piece of group interaction here. Let A0 be maximal such that we take a set that the subsets of kappa are ordered by inclusion. And what I'm claiming here is that if we look at homogeneous sets for the color R0, for example, that this family of subsets has maximal elements. So group interaction Y is Zorn's lemma applicable. You will find that question on the file. Okay. So what do we do? Well, what happens if we have an alpha in A0? Okay, it's conceivable that A0 is empty, that there are no R maximal sets, but then everything is blue, and so we really have a big blue homogeneous set. So let us assume that at least a few lines are red, and start from there. What do we know if alpha is in A0? Well, then B alpha, well, it is disjoint from A0 because all the lines from alpha going to the other points of A0 are going to be red. That's one thing. The other thing is, if beta is not in A0, then beta is an element of B alpha for some alpha in A0. Why is that? That is by maximality. If all the lines from beta to A0 were red, then we could add beta to A0 and A0 wouldn't be maximal. So we get roughly this picture. Okay, let me. Okay, so here is A0 and all the lines. Okay, all the lines between all those points are red. And if I take any point outside A0, then I must be able to find a blue line that goes out of that, from that beta into A0, and that line has to be blue. Okay, so what do we get? We get that kappa minus A0 is the union of all the B alphas, where alpha is in A0. Well, regularity the cardinality of kappa minus A0 is kappa because A0 is small, and that's it. we can take an x0 that has very many blue neighbors. So what do we do now? Well, we take a maximal set that is red, but now we take it as a subset of bx0. And we get the same story. And it's only maximal as a subset of bx0, by the way, because we forget about the rest. We concentrate on bx0 for the rest of the proof. There is an x1 in A1 such that bx1 intersect bx0 has cardinality kappa. We do exactly the same thing inside bx0. We get an x1 and the whole thing repeats itself. And now you can find the recursive step. And shall we see, if we go from n to n plus 1, take a n plus 1 And by the way, because of our assumption, this never stops. In the end, we get okay. And now I want to, before lest I forget, we cannot expect to go any further than omega. You might think, well, why don't we take the intersection of all the bxn's where n is in omega and just keep going? Well, the problem is there is no guarantee that the intersection of the bxn's is even non-empty. You could make a sort of a tricky partition whereby you look at every ordinal and look at its place in the look at the limit, the largest limit below it, and the natural number that has to be added to the limit to get your x. And you can probably create something so that the bxn is all the ordinals with natural number part at least n, and then the intersection of all those things is just empty again. And so the proof really stops here. If we assume that we have small red homogeneous sets, then this is how far we can get. We can get an countably infinite blue homogeneous set and nothing more. Case 2, kappa singular. And like I said, there is a point here where you can actually jump in and say, well, but this could also work for kappa regular. And that is something that I would like you to mull over during the group interaction. Because this case splits into two cases. And the case kind of looks like what we just did a few moments ago. This is a rather strong assumption, but nevertheless, it's we're going to do an either or. We're going to do this assumption or its negation. Then you can actually go through what we did above without all the maximality stuff. Take an x0 in X with this property, and then you keep going. You can take an x in an xn plus 1 in X, and in the intersection of the previous bxi's, and with this property over here. Or you could simply say we apply this to that big set over there. And then you get the countably infinite homogeneous set for the color blue again. So how do we get the possibly the homogeneous set of size kappa? Well, that's case 2b, not case 2a. There is an X such that, well, the cardinality of X is kappa, and Bx intersect X is less than kappa for all X in X. Simply case 2b is not case 2a. And now we're going to try and find a homogeneous set of size kappa. Since we know that in the opposite case we have this infinite thing, we can also assume that there is no infinite, oops, I'm sorry, not red. No infinite blue homogeneous set. If there is an infinite blue homogeneous set, we're done. So we assume that we don't have any blue homogeneous sets at all. Okay, now what? And we can also, without loss of generality, simply say that X is kappa. We just forget about the rest of kappa and work inside X. Okay, group interaction. Well, show how to construct a red homogeneous set of cardinality kappa. And compare your proof of that with the proof that I'm about to give now. You will see that there is, shall we say, a difference in length between the two. Okay, we assume kappa is singular now. And so what do? We need to set up a few things. And I think I will do one thing and then we'll have the break and then I'll finish the argument. Let's see, I want to keep all my letters straight here. Okay, our cardinal is singular. Fine. So it's the limit of a short sequence of cardinals. We can replace all the cardinals in that sequence by their successors, and we can make that a sequence of regular cardinals. That's this assumption. And all the cardinals below the cofinality of kappa, including the cofinality of kappa, are not important. We need a sequence that starts above the cofinality of kappa. All that is easily arranged. But to make the construction that I'm about to do go a bit smoothly, I'm going to do a sort of a lemma. And in preparation of the recursive steps that we're going to do, we do this. We take a regular cardinal between cofinality of kappa and kappa itself. Could be one of the kappas. Why not? We let X be a subset of kappa of cardinality lambda. And now we have our assumption. We divide X into subsets. Well, not quite divide. It's an increasing union. Notice that that was our assumption about the points. We have replaced x by kappa, but the assumption is that every blue neighborhood, so to speak, is small, smaller than kappa. That means that if we take an alpha in x, then its blue neighborhood is less than or equal to some kappa eta. So we get that x is the union of those x etas. But lambda is bigger than the cofinality of kappa, so there is an eta. So what do we get? We get an eta that is big, of size lambda. But what we also get is that b of x eta, and we can imagine what that is what that means. If you have a subset of kappa, you can look at all the blue lines emanating from that set, and we call the ordinals where they end up. We call that the blue neighborhood of the set x eta. This set, what's the cardinality? At most what? Well, lambda times kappa eta, which is the maximum of the two, but it's still way smaller than kappa. It's either the lambda or the kappa eta. And if and we have one more thing. Remember, we assumed that all the blue homogeneous sets were finite. So all the blue homogeneous sets of x eta are finite. Now we apply the regular case. Which says that x eta has an R homogeneous subset. What shall we call this? Well, call it y eta of cardinality. Cardinality lambda. So what does this accomplish? Well, and this is what we'll be using in a moment. If we have a regular cardinal below kappa, the regular cardinal is bigger than the cofinality of kappa, then every subset of kappa of size lambda, every subset of size lambda has an R homogeneous subset of size lambda. Let's call it Y. Okay, that's no surprise, but also the blue neighborhood of that set is relatively small. Relatively small meaning cardinality less than kappa. So yeah, what does this look like? I'm going to draw a sort of a weird picture. Here is our subset of size lambda. And here is the really, 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 really big subset of size lambda, again, where all the lines are red amongst all those points. But if we go outside this set with our blue lines, we look at all the blue lines that go outside this red set, then this set here, the set of endpoints, is small. And this is the thing that is going to help us to create the red homogeneous set of size kappa. You're probably going to see some parallels with the construction that we gave a few moments ago of the other homogeneous set. And we'll do that in about 10 minutes, shall we? We'll have a toilet break and we'll reconvene at about 3 o'clock or something like that. And I'll pause the recording. Resume the recording. Yes, there we go. So here is the crucial statement that we proved just a few moments ago. If you have a regular cardinal less than kappa, but larger than the cofinality, then you can find within every set of size lambda an R, a red homogeneous set of the same size, but with relatively small blue neighborhood. And once we have that, the construction is, should all be careful with those kind of words, but it is relatively straightforward. Thanks to this setup. And I'll try and draw a picture to go with the construction. Let's see how. So this is kappa. This is kappa 0. This is kappa 1. Here is some kappa eta. And okay, so the kappas increase and eta could conceivably be inaccessible, but we never know. So here somewhere is the supremum of all the smaller kappas, and we get this this big subset of size kappa n. So this this set is called A0, this set is called A1, this set is called A eta. So A eta is the set kappa eta minus the union the kappa gammas. And this union, this supremum, is strictly less than kappa eta because kappa eta is regular and eta is less than the cofinality of kappa. So this union can never have cardinality kappa eta. That is something that we should remember. Okay. And every A eta has cardinality kappa eta by this regularity thing. So here is the setup. So, well, what do? We have our lemma, so to speak. So here, inside A0, there is a big homogeneous set, H0. So we take We take a subset of A0, cardinality kappa, red homogeneous, and the blue neighborhood of H0 is small. Okay, lovely. So here is our H0, and there are very few, relatively speaking, blue lines emanating from H0. Okay, let me put H0 here. Okay, so H0 is going to be part of our homogeneous set. So where is that homogeneous set going to come from? What's the next piece? Well, like I said, the cardinality of BH0 is small. So what do? We take eta 1. Yes, was that my notation? Yes. The cardinality of the neighborhood set of the blue neighborhood of H0 is small. That means that it is smaller than a certain kappa eta. Well, we take the first eta above eta 0. Well, eta 0 is just 0 in our case. So we just take the next eta up if necessary, such that the cardinality of that neighborhood set is less than kappa eta. Well, just for the picture, let us assume for the moment that eta 1 is equal to 2, but of course there is no real reason for that. So what do we get? We look at the blue neighborhoods of H0, and that is a very small portion of A2. Okay, there may be blue neighborhoods of A0 here as well, of H0 here as well. And this might even be kappa 1, many of them. But here we have fewer than kappa 2, many blue neighborhoods of A0, H0. Well, what does our lemma say? We can find an H1 take okay, let's make it red. We take H of eta 1, we throw away the neighborhoods, the blue neighbors of H0, and we take a red homogeneous set inside that complement, which we can do. And what do we want of those things? Well, we wanted to have cardinality. Kappa eta 1. We want it to be red homogeneous. And we want its neighborhood to be small. Its blue neighborhood, we want it to be small. Now, what's the result of our exercise? Well, we have two red homogeneous sets, but all those sets in H1 are not among the blue neighbors of H0. So all the lines between all the points of H0 and H1 are red. We took all the possible blue lines out of H0, took the corresponding neighbors, threw them away from H2, all the other red lines emanating from H0, all the points here have red lines connecting them to H0. And now you can see where this is going. In general, so if our construction has been going for a while, we have all those H gammas where H gamma is a subset of A. How do we call that? Eta gamma somehow. All the blue neighborhoods are small, and because delta is less than the cofinality of kappa, we still know that X is of cardinality less than kappa. We have a really small set of sets of a small family of sets of small cardinality. So the union is still of small cardinality. And now we do the same thing. Take the first eta delta above the eta gammas, such that A eta delta minus X still has, as carbon, no, this is not what I want. Such that the cardinality of X is less than kappa of eta delta, and then take our homogeneous kappa thingy and the neighborhoods. There are still few blue neighborhoods of that, and keep going. And so just to complete the picture up here. So for example, this was eta delta. So here is H delta. And what do we get? We get that all the lines going here and all the lines going over there, they're all red. So H0 union H1 union H union H delta is still red homogeneous. And this construction this construction lasts cofinality kappa many steps. The cofinality of kappa is regular. Whenever we are before cofinality of kappa, the union of all the sets that we have is of cardinality less than kappa. So there's always room to go one more step. And because the cardinalities keep increasing, we get that H has cardinality kappa, H is red homogeneous. So there. And that's the end of the construction. And now when you do the group interaction later today or later in the week, and you try to work this under the assumption that kappa is regular, you will see that you need only, I don't know, 6, 7 lines to construct the homogeneous set of size kappa. And that should let you appreciate the pleasure of working with regular cardinals as opposed to singular ones, because this was way much more work than in the regular case. What kind of thing can you apply this to? Well, Dushnik and Miller were investigating partial orders, and so they here is an application. If you have a partial order, then either, okay, of cardinality, if you have a partial order and you look at it and you try to find linearly ordered subsets, chains, then either you can find one of cardinality kappa, but if you cannot, then there is an infinite set I such that if you have a partial order, then you can find a chain of the same cardinality. And if you cannot, then there must be an infinite set such that all pairs of elements are incomparable in the partial order. You could formulate this in a slightly more positive way. You say, well, if I have a partial order where all the incomparable sets are finite, well, then I should expect a chain of full cardinality. And I'll leave you to think what the partition should be that will tell you that this is going to happen. Okay. So this is the Erdős-Dushnik-Miller theorem on partitions, and we leave the partitions aside for the moment. I saw in the chat that there was a question. Yes, but why doesn't this give us something like this? Why the lopsided thing? Well, like I said, the proof will give you not more than this. And the examples that we gave of, say, the reals and Aleph-1, and so they tell you that it's not easy to get this situation. And actually, we'll get back to this, I hope, at the end of class, when I'll introduce weakly compact cardinals. And then you will find that this is actually a rather special and very strong assumption to make on cardinal numbers. There are some variations of the Dushnik-Miller theorem, but I'll leave them aside for now. because we are going to talk about our next subject, which is also something set up towards the large cardinals that we'll be talking about in the rest of the course. And we'll be talking about trees. And so first thing, what is a tree? Well, and trees are also used in the theory of the partition calculus, by the way. So there is a connection between what we did and what we'll be doing now. It's a partially ordered set, and when it's a tree, we call it T, we don't call it P, with the following property. So a tree is a partially ordered set, fine, such that if you look down from a point, you will see a well-ordered set. You look down and you see something well-ordered going down. So what does a tree look like? Well, if I have a point in my tree and I look down, then this should be all the things that are really strictly below our point X. They should be well ordered. So in particular, they should be linearly ordered. So when you look down from X, you see, you don't see the things that are incomparable to X, you only see the things that are below X, and that they form a nice linearly ordered set. Not only that, it is well ordered. It also means that, say, if you have 2 points that are incomparable, well, they could possibly meet below X and Y. So you could look at all the things below X, you can look at all the things below Y, and there could be a point that they have in common, and then everything below that they will have to have in common as well. But the important thing is that there is nothing above both X and Y, because if there was a Z that was bigger than X and bigger than Y, then X and Y would have to be comparable because of this linear order down there. So when you look above, when you look up from 2 points, you look at all the points that are above X, you look at all the points that are above Y, then they have nothing in common. So the tree really looks like a tree. Any sensible tree that I'm looking at right now through the kitchen window looks like a tree in mathematics. I haven't seen 2 branches grow together again. So this is the structure that we're talking about. We have some notation and some examples, but I'll give the notation first and the examples later. And the notation, I will try to follow as much as possible the notation in Yech. So if I have a point in the tree, if I have a point in the tree and I look down, I see something well ordered. Okay, I write down the order type and I call that O of X. Alphath level I tend to write T alpha for this. Yech doesn't actually have a word, have a name for that, which I think is unfortunate, because level is being used all the time. The height of the tree is the supremum of all the OX's plus 1. So it is the smallest ordinal that is bigger than all the OX's for X in T. I just have to write down these words because I'm using them all the time, and I want to make sure that everybody is on board, at least what those terms mean. A branch is a maximal chain. So a branch goes simply, it starts at the bottom and it goes all the way up until it cannot go any further. And of course, alpha branch of order type alpha. I think those are the words that we need for the rest of today. And if there are any others, I will define them as needed. Some examples. Well, really non-standard examples are hard to come by, as we will see in a moment, but you have already seen a few examples here and there because we were looking at maps from ordinals to cardinals when we were doing the cardinal arithmetic. So for example, notice this notation. The set of all the functions from natural numbers to 2 for some people, this is the binary tree. It has a root, the empty sequence. The root has 2 successors, the sequence that just 0 and the sequence at just 1. That has 2 direct successors, 0, 0, 0, 1, 1, 0, 1, 1. And now you see why people don't really go all the way up, because the thing gets more and more complicated the higher you get. So the next level of this tree will have 8 points and so on. What are the branches? Well, every branch determines a function from omega to 2. And conversely, if you have a function from omega to 2, then you can define a branch in this tree. X will give you all the restrictions. You restrict X to 0, that gives you the empty sequence. You restrict it to 1, that'll give you the sequence 0 or the sequence 1, and so on. And this is a branch that goes all the way through the tree. That would be the branch that goes with X. And if you have a branch, it means that all the sequences are initial segments of each other, and you can take their union and you get a function from omega to 2. The height of this tree is omega, because we get all finite numbers. And in the same vein, we can take there is no reason to restrict ourselves to the ordinal omega. We can take any ordinal here. So you can put your favorite ordinal over there, and then you look at all the sequences that are shorter than your favorite ordinal, and that will form a tree. The height is your favorite ordinal, and branches will give you functions from your favorite ordinal too. Well, if you have branches that go all the way to the top, they will give you functions from your favorite ordinal to A, for example. Here is a, shall we say, well, here is a special tree. We can look at a subtree. Let's make this black. By the way, the ordering of those sequences is simply by extension. So if I have a function defined on ordinal alpha and a function defined on ordinal beta, and beta is bigger than alpha, then simply extension of functions is the ordering. We can take a subtree of the reals. We can take the real line and take all the functions from all the countable ordinals to R. And we can, for example, take all the S's. S is strictly increasing. What can we say about this tree? Well, the order, the height, or what you call it, of a, this is also true for the trees that we just looked at, by the way. The order type of the predecessors of your sequence is just its domain. That's the ordinal that'll tell you what the height is. What's the height of the tree? Well, the height is omega 1. Why is that? Well, you can, I think we haven't proved it yet, but we'll see in a moment actually that it is true. You can embed every countable linear order into the reals. In particular, every countable ordinal can be found as a subset of the real line. And with it goes one of those strictly increasing maps. So for every alpha, there is a member in our tree of height of order alpha. But no longer, because we know that there is no increasing omega 1 sequence in the real line. So we don't get above beyond omega 1. There are actually no omega 1 branches. Because an omega 1 branch would give you a strictly increasing map from omega 1 into the real line, which doesn't exist because that's the basis of Sierpinski's example. Okay, those are some examples, and now we get to one of the important lemmas of today. Well, actually, what I'm talking about today is important, of course, but this one sets up a definition that will lead to large cardinals again. And it is König's infinity lemma. And I actually, before I write it down in our language, I would like to show you what König's infinity lemma actually says. And here it is. I copied this from the first page of the paper, and the statement of the theorem is here. And if you read any German, you will see that there is no mention of trees whatsoever, because what I'm going to talk about is a version of this result. But what I want to draw your attention to is this. The title of the paper is not something like trees or relations or whatever. It says how we can reach conclusions about the infinite, how we can take conclusions from the finite into the infinite, roughly is a rough translation of what it says. And the proof of this theorem is not very long, and you will see that it's not very long when I give it. But the nice thing here is the subtitle of the paper, Punktmengen, Kartenverben, Verwandtschaftsbeziehungen, das Schachspiel. He gives applications of this theorem to all kinds of combinatorial problems where you have a finite solution and you'd like a solution to the infinite version of that. And this is what the theorem allows you to do. In some sense, it also allows you to go the other way. If you have something infinite, you can bring it down to the finite. You can get sort of the compactness result from logic, for example. And I'll mention a few consequences of this theorem in a moment. But how do we formulate it? As follows. Because we're talking about trees, we'll take the tree version of Koenig's lemma, but you can take his original version and get it from the tree version. And this original version implies the tree version as well. If you like that kind of thing, it's nice to work out the relationship between the two statements. So Koenig's, this is, by the way, the son of the Kőnig that we talked about a few lectures ago, the one with the inequalities for the infinite cardinals. This is his son who proved this finite, countable finite lemma. Let T be an infinite tree. Finite levels. So whenever you take a level of your tree, it has only finitely many points. And then the conclusion is then T has an infinite branch. And we only need an infinite chain because then you can extend it to a branch in the tree if you want. You can use Zorn's lemma for that or any other choicey principle that you like. So we'll construct an infinite chain and then you can go higher up in the tree if you want to get your infinite branch. Okay. So how does the proof go? The proof is not very long, but in the group interaction, I will also ask you to reflect on this proof because, well, you will see in a moment why. And it goes as follows. Look at T0. T0 is the bottom level of the tree. It's all the points whose O is equal to 0. That means those are points with 0 predecessors. And like I said, it's the bottom level of the tree. It's finite. Okay. That means that the union of all the following sets look closely. We take all the x's from T0, that's finitely many of them. For every x, we look at the points above x. And so what is this? That's just T except for T0, because every point sits above a point of level 0. This set is infinite. Well, there you go. There must be a point on level 0 at the base, at ground level, where it has infinitely many things above it. Now, you can see where this is going, because now T1 is finite. And the union of all those sets this set is infinite because it covers, it is the y's above, it's the it's all the points above x0 take away T1. Well, T1 is finite. There you have it. So there you go, big. And now you can see what's going to happen at every stage of the recursion. Once we are at level n, we have a point there with infinitely many things above it. We take xn plus 1 in tn plus 1 with, well, xn plus 1 bigger than xn. And of course, with all those, with that set infinite. And then xn is an infinite chain. And sits in an infinite branch. Okay, so that's the statement and proof of Koenig's lemma. And if you look in Koenig's paper, you will see that the proof is not much longer or shorter than what I have just written down. You basically follow your nose and you say, well, yeah, of course, this is going to happen. So what about the group interaction? The group interaction asks you to look at this proof a bit more closely and figure out where the axiom of choice is being used, because it is being used in this whole process. There is a portion of the axiom of choice that is needed to make this work. And I really, really want you to reflect on that. If I won't forget, I'll mention something about this next week, but I do like you to think about this for a bit. That the proof is so simple because I have hidden the axiom of choice to some extent. Okay, before we have to break, let me mention a few consequences of this. What were the applications, for example, that Kőnig proved, and then we'll get to further things related to trees. Well, you can prove Ramsey's theorem using König's lemma. You may wonder, well, you can prove Ramsey's theorem without König's lemma. Well, not quite. If you prove the infinite version of Ramsey's theorem, you also prove König's lemma. And you can apply König's lemma in a suitable proof of Ramsey's theorem. And in the homework, there is a proof of the easiest version of Ramsey's theorem using König's lemma. But you can actually do all versions of Ramsey's theorem using this lemma. It's a very powerful tool, by the way. The Punktmengen that you could see in the copy of the first page of König's paper, what he was referring to is, okay, you have seen this in analysis, the closed unit interval, the real unit interval is compact, and you can prove that using König's lemma. And conversely, you can prove König's lemma using compactness of the unit interval. So König's lemma and the compactness of the unit interval, more generally compactness of closed bounded subsets of Euclidean spaces, that is equivalent to König's lemma. Compactness in logic. Okay, in this case, you have to confine yourself to countably many formulas in a countable language, because König's lemma only gives you a countable branch, but there are certain extensions of König's lemma that will give you the full compactness of logic. And I put this in quotes, compactness in combinatorics. If you have, say, a graph where, and this is for the people who've done some graph theory, but if you have a graph such that all finite subgraphs have say a coloring with 10 colors, then the whole infinite graph has a coloring with at most 10 colors. And the coloring means that connected points get different colors. If you don't know about graph theory, forget about this. But this is these are some of the applications that you can find. Like I said, it's a very, very powerful result. And before we have our break, our toilet break, I will ask a question that you can think about and see if you can prove it. What about LF1? So what did we have what did we have? We had an infinite tree with finite levels, and we got a chain that we got an infinite chain. So now we replace infinite by uncountable and finite with countable. So uncountable chain, countable levels. All we did was take the assumptions of Koenig's lemma and push them up one cardinal. Is there an uncountable? Well, chain or branch, that's the same thing. If there's an uncountable chain, we can extend it to an uncountable branch. And if we have an uncountable branch, that is an uncountable chain. So that's the question. And I'll leave you to think about that for 10 minutes while I also need to go to the loo, by the way. Okay, let's pause the recording for a moment. And I would like to see the menu. Yes, there it is. And you did?
Yep, started now.
Okay, lovely. Okay, so we're back to our problem of just a few moments ago. What about LF1? And well, let me give you the answer. Where is it? Here it is. Oh. This is from a paper of Kurepa in the 1930s, where he quotes Aronszajn, who gave a counterexample to this question. And this is, as far as I can see, the only place where this proof of Aronszajn has appeared. There appears to be no paper by Aronszajn himself where this answer is given. And it's a footnote in Kurepa's paper. That paper is all about trees and ramifications, and also some partition calculus is done there. I'm not going to translate this French bit for you. I'm going to give a slightly easier argument than the one in the footnote here. So the answer is no. So let me write that down to begin with. There is a tree, A, for Aronszajn, cardinality LF1, countable levels, so since the levels are countable and the cardinality is LF1, the height is also omega 1, and no omega 1 branches. And we have already seen sort of a prototype of this, which has all the three properties except for two. That was the tree of all the strictly increasing maps from countable order to the reals. That tree does not have cardinality LF1. It doesn't have countable levels, but it has no omega 1 branches. But it does have height omega 1. So there is a sort of a precedent. You can have a high tree where all the branches die out. So there are branches of arbitrary countable length, but none of them goes decidedly all the way to the top. So it's not completely impossible that there are no omega 1 branches while the tree is omega 1 high. So how do we create such a tree? We could start with the increasing sequences of real numbers, but that is slightly inconvenient. We start with the rationals so we take all possible sequences of rational numbers whose domain is a countable ordinal. You may want to see how you could use the real line as a codomain. It can be done. You could cheat and say, I take the real line as a codomain and only look at rational sequences, but there are things you can do with the real line that you cannot do with the rational line. But I won't go into that.
Question.
Yeah.
Is that just the power set of the rationals?
Pardon?
Consider Q to the power of small omega 1. Is that just the power set of the rationals?
No. It's all the sequences of rational numbers whose domain is a countable ordinal.
Oh, yes.
You could also actually use subsets of the rationals. I'll probably say something about that later on, but we'll simply look at all the strictly increasing functions from countable ordinals to the rationals. Because first I took all the sequences, but that's too many. We start with we take all the strictly increasing members of that tree. And like I said, every countable set can be embedded into the rationals. So that means for every countable ordinal, there is at least one strictly increasing map into the rational. So this tree is really is already of height omega 1. But we'll see that in our construction anyway. So this one has height omega 1, that's good. No uncountable branches. Obviously, because an uncountable branch would give you a strictly increasing map from omega 1 into the rationals, an injective map from omega 1 into the rationals, and that's patently impossible. But there is a slight snag here, every level. Okay, every level, but from omega and up. As cardinality. 2 to the L of 0, which is not quite countable, and we would like to have a countable. We would like to have countable levels. Well, in actual fact, what we're going to do is we're going to thin out this huge tree I and thin it out so that we get a subtree that has only countable levels. And of course, because it's a subtree of I, it will not, it will not have any branches of length L of 1. So how do we do that? We build a subtree of I. Height omega 1. Its levels all the levels countable. And how do we start? Well, we start rather modestly. The 0 level is just the empty sequence. Okay. The rest of the construction will be slightly more involved. Okay, I'll show you what A1 will look like. A1 will consist of all sequences of rational numbers of length 1. This is my notation for sequences like this. So A1 is countable. And okay, that's a good start. You can imagine what A2 will look like. We still have basically no restrictions, so we could do Q0, Q1. We can take all the ordered pairs, all the sequences of length 2, so to speak, that are strictly increasing. And this is still countable, and this is a good start for our tree. Our tree, so it looks like 1 point at the bottom, and then infinitely many points at the next level, and every one of those points has infinitely many direct successors. It looks like a pretty bushy tree, certainly at the beginning, with all those infinitely many direct successors. And you can fill out what A0, what A3, A4, and A5, and so on will be. What we will do, and I'll put a star here in front, we will do the construction, and maybe I should lower it a little bit. So here we go. We're going to construct the levels, and while we do the constructing, we make sure that the following always holds. And when you look at our beginning, you will certainly see that that is always satisfied if alpha is less than beta. If S is in A alpha, then S is bounded. So if we have a member of our, if we have something in our, on a level, then it is a bounded sequence. So it's a bounded, strictly increasing sequence. And if you give me a rational number, Q is always a rational number, that is bigger than the supremum of the range of S. We can take the supremum in the real line and then look at all the rational points above that supremum. Then what? There is a T in A beta, such that what? Well, T is an extension of S, so T is a beta sequence of rational numbers, S is an alpha sequence of rational numbers, and S is an initial segment of T. Okay, and if I take the supremum of the range of T, then that is also less than Q. Okay. Okay, we can want this, but we have to make sure that we actually can do this. But this is the way we intend to complete the construction. Whenever we construct a new level, we make sure that this holds with respect to every lower level as well. And so how do we do that? Well, we have, of course, two cases. We have the successor case and we have the limit case. The successor case is easy. If we have A alpha and we build A alpha plus 1, then this is, like I said, it's quite simple. Look at our demand. We want to make sure that we get as close to the supremum of the range of S as possible at the next level. And so this is what we do. And how shall I write this? So this little thingy, this little bridge or whatever you want to call it, is the concatenation operation. So S is a sequence, let's say, is an alpha sequence, and S with Q is the same sequence. Where we, this is the domain of this is alpha plus 1, and up to alpha, it has the same values as S, and the value at alpha is that value Q. Okay, so we simply tack every rational number bigger than the supremum of the range of S. We tack it at the end of our sequence S. We do that for every sequence in A alpha. Now, if A alpha is countable, that's one assumption that I should have mentioned too, but that was one of our goals. Is A alpha countable? Then A alpha plus 1 is countable as well. That's good to know. And we have star. And so suppose we have beta less than alpha plus 1. Well, beta could be alpha. Then there's nothing to prove because we just made damn sure that we had all the things bigger than the supremum as our last item in the list. And if beta is less than alpha, then if we have an S over here, we get a T over here with the supremum of the range smaller, and we have a Q that is bigger than the supremum of the range of S. We know by our assumption star that we can make sure that the supremum of the range of T is less than Q. And then, of course, we can take T with a P, where the P is less than Q, but still bigger than the supremum of the range, because between every two real numbers, there is a rational number. Okay, so that's not too hard, but what if alpha, okay, let's use another letter. Suppose we have constructed our levels A alpha up to some limit delta. And so now we must make A delta. How are we going to do that? Well, I'll try and draw a picture. This is delta, and we have found our A alphas all the way up to delta, and we have a point S here. And one of the things that we need delta is a countable limit order, and also it has a sequence that is cofinal in it. We need that in order to be able to walk up to level delta. Okay, we have an S here, and we have a Q that is bigger than the supremum of the range of S. Now what? Well, Q is arbitrary. So what do we do? Well, here's our S. And S sits above level beta 1, so we don't really worry about that. But on level beta 2, there is an S2 there is something on level beta 2 who's such that supremum of that range is less than Q2. That was our assumption star. Okay, let's call this beta 3. On level beta 3, there is an S3 such that the supremum of the range of S3 is less than Q. That's our assumption star applied to S2. Now, we can see where this is going. We can take Sn plus 1 in A beta n plus 1. Sn plus 1 extends Sn, and still the supremum of the range of Sn plus 1 is less than Q. At every stage, we can keep on doing this. And then in the end, we have an increasing sequence of sequences. We can take the union, that is a nice function, whose domain is delta because the supremum of the betas is delta. Of course, it extends S because we started out with something above S and kept on extending that. And okay, the supremum of the range of T is less than or equal to Q. But Q is arbitrary. So for everything that is above the range of S, we can find something less than or equal. And so we could have taken something, we could have taken a P between Q and the supremum, and we could have stayed below this P all the time. And then in the end, we would have gotten less than or equal to P, and that would still be less than Q. So that's not really the big thing. And this T, for the moment, we write it as the T of S and Q, because we started with an S, we started with a Q, and using that, we build our T. And now we see what A delta is going to be. That's going to be all the things we can construct in this way, well, all the levels A alpha were countable by assumption, and the union of all those levels is still countable, so this is a countable set. And we still have star by construction. Why do we have star by construction? Well, we took an arbitrary S, we took an arbitrary Q, and we found for every pair, we found something on level delta that would extend S, and the supremum of the range would be less than or equal than that Q, but because arbitrariness of Q and the density of the rationals, this is enough. And that's the construction of the tree. It looks simple. It is simple, but it took a while before people actually thought of it, because probably for a while they thought that you could extend Koenig's lemma to larger cardinals by simply going through the proof. But when you try to prove Koenig's lemma for LF1, you end up in the same type of trouble that we got with the Erdős-Dushnik-Miller theorem, where we constructed an omega sequence that was homogeneous for blue, if I recall. And along the way, we constructed the decreasing sequence of sets of size kappa, and we had no guarantee that the intersection of that family was even non-empty. And the same thing will happen when you try to prove that there are no Aronszajn trees, because this tree is called an Aronszajn tree in honor of Aronszajn. If you take your uncountable tree and you go through the proof of Koenig's lemma, you say, okay, at the bottom there is a point with an uncountable thing above it. Go one up, uncountable thing above it. Go one up, uncountable thing above it. And before you know it, when you get to level omega, when you look at this proof, when you get to level omega, you could have been careless and you would have ended up next to, but not equal to, none of those T's that we have constructed. You could have gone along a branch that simply died out. It would end here, and that would be it. Because in the, like I said, in the first levels, if you take all possible strictly increasing sequences of rationals, the omegath level has cardinality 2 to the L of 0. What we have done is take a very careful selection of L of 0, many members of that really big level, and used only those to continue our construction. And the possible proof will die at one of those levels because you just missed all those countably many points that we actually put in. So the answer to the question, what about LF1? The answer is no. And this gives us a definition of a property which, okay, it's not very original, but it's called the tree property. And the tree property is actually yes to Koenig's lemma. Kappa, a cardinal, has the tree property if every tree of cardinality kappa with levels of cardinality less than kappa has a kappa branch. So the tree property means, and usually kappa is assumed to be regular. Kappa has the tree property if what? Every tree of cardinality kappa with levels of cardinality less than kappa has a kappa branch. So what is Kőnig tells us? L of 0 has the tree property. Aronszajn L of 1 does not. And so now what? What about L of 2? Does it have the tree property? Continuum hypothesis implies no. From if you have the continuum hypothesis, you can find an L of 2 Aronszajn tree. So if you're willing to assume the continuum hypothesis, L of 2 does not have the tree property. Without CH, things get interesting. And I'll come back to that later because I have to make a definition first before I can tell you how interesting things are going to get with the cardinal L of 2. But it is, things get really difficult when you try to talk about Aronszajn trees of even higher cardinality. Although the generalized continuum hypothesis will tell you that no uncountable cardinal, no uncountable below the first inaccessible for sure has the tree property. And actually, you can go way, way higher until you meet the tree property at last. But let's not get into that. I want to make one or two remarks about the construction that I just gave. Variations on the construction. You can ensure that if you do the construction of the Aronszajn tree a little bit careful, you can actually make sure that every sequence has as the supremum of its range a rational number. This is clear if the domain is a successor ordinal because all the values are rational numbers, but you can make this also happen for the points on limit level. Somebody asked you something about subsets of the rationals. You can actually take the following you can forget about the functions and you can think about all the subsets of the rationals that are well ordered by the normal ordering. And you can say that A is less than B if A is an initial segment of B. This is also a tree. You can verify that, and you can do the construction inside this tree as well. Actually, the tree is more or less the same as the tree that we looked at, but it is one slight level of complexity lower. There are no ordered pairs in the functions. And you can also start out by saying, I'm taking only the well-ordered sets whose supremum is a rational number, or whether they are unbounded. And then the construction goes through. You can do the same thing with the reals and do similar constructions. Okay, let's see how far we got. We have a property of Aleph 0, the tree property, that fails for Aleph 1. We have seen other properties of Aleph 0 that fail for Aleph 1, or the other way around. Aleph 0 has a decreasing map that is almost injective. If you, not a decreasing map, a regressive map. We have the pressing down lemma for regular cardinals. If you have a function that presses down, that it is constant on a stationary set. But we also have, of course, the following. We have Ramsey's theorem. And we have the failure of Ramsey's theorem, a really strong failure. It fails for 2, for Aleph 1. So here's another thing. We have something that is true for Aleph 0, and we have something that fails for Aleph 1. And of course, here the situation is clear. No axiom of choice needed. For no successor cardinal can we have Ramsey's theorem. If kappa is singular, I think we have seen that kappa doesn't arrow itself either. The idea is that if you take kappa and split it into small subsets of subsets of small cardinality, then you color a pair red if they are in distinct sets, but you color the pair blue. Okay, let me erase that. If 2 points are in different parts of the partition, like we saw in the proof of the Dushnik-Miller theorem, we call them red. If they're in the same, we call them blue. Homogeneous sets are small. A red homogeneous set is at most the cofinality of kappa, and a blue homogeneous set is at most one of those intervals. So there you have it. Kappa doesn't arrow kappa, and I should put a bar through this arrow over here. So getting kappa to arrow itself is a little bit difficult. And that gives us a definition. And here is the next shall we say, large cardinal property that we'll talk about. And it's a quarter till, so I'll probably end with the definition, and I'll announce one or two things that are going to happen next time. We call a cardinal weakly compact if it is uncountable, although we could argue that L of 0 is weakly compact as well, but L of 0 is a special case, and we're only really interested in the uncountable case, so we'll take uncountable on board. And if we get this arrow relation, and what we have seen already is that apparently it cannot be a successor cardinal, cannot be a singular cardinal. So it must be at least a limit cardinal, and we have already seen that 2 to the kappa doesn't arrow kappa plus. So is already strongly inaccessible. It's a regular it's a limit, it's a regular limit, so it's inaccessible, but it's also a strong limit that we can see just by looking at the counterexamples that we found for the partition relation. So it's a large cardinal. What we will see next week is that weakly compact that the tree property does appear again. Weakly compact means that you need to be strongly inaccessible and have the tree property. And we will see that this implies that the weakly compact cardinals are way bigger than the first few inaccessible cardinals. There are tons of inaccessible cardinals below a weakly compact. They're really big as compared to what we have seen so far. Okay, that is what I had to say today. And Ned, if you can stop the recording, please, then I'll end